So hello everyone. Today we are pleased to have Gaëtan Hadjeres speaking. He graduated from École Polytechnique and then got his PhD in interactive deep generative models for symbolic music in Sorbonne University, and he is now a permanent member of the music team at Sony CSL. And he will talk about his recent work on Piano Inpainting Application. So thank you for accepting to present your work, Gaëtan, and the floor is yours.
Yeah, thank you, David. Hello, everyone. So I'm Gaëtan Hadjeres. I'm working at Sony CSL, and today I'm glad to present the Piano Inpainting Application. So it's an Ableton plugin meant to assist the creators when they are composing piano performances. And so I hope it's another way to compose piano in a playful way. So what's the motivation behind this? So my objective when doing AI music is to create AI that can be seen as creative assistants. So when you are thinking about an assistant, it means that you have an artist dialoguing with the AI. And so I'm less interested in just AI that can produce an infinite amount of music, but more into building tools that can be used by artists. And so in this work, I will focus on music, and especially on symbolic music, so scores or piano performances. And so the main question is, can artificial intelligence assist us when we are composing? And so for me, like, this implies that you have to create some kind of interesting dialogue between an artist and the AI. And with this in mind, we could say that the artist now becomes some kind of artistic director, because they just have to choose and dialogue with the AI and just validate or invalidate some like proposals by the AI. And so we can wonder what can be the good ingredients that can engage artists into dialoguing with an AI. But first of all, do we really need AI assistants to compose music? Because like you have like plenty of people who are able to compose music, and so they might not need such assistants. But for example, for piano music, it's quite hard to compose a piano piece, because even if you are an expert, so which requires a lot of time and a lot of training, you would still need a lot of time, because it's quite lengthy to write all these notes, and you would still need to be some kind of an expert. And so my idea when creating AI assistants is that the AI can deal with the technical parts. Because when you are composing music, you have a whole process when you start from a blank sheet to like a fully composed piece. And some parts are less creative, I would say, than others. And so the AI could deal with those parts. And there are two benefits for this. It's like you could make with an AI assistant music composition accessible for non-expert musicians. So even if you can't play the piano or can't like read the score, you can still say, oh, I like this, I don't like this. And you can start dialoguing with an AI, and at the end you will be able to produce your own track, even if you have no like classical expertise, so to say. Also for experts, it could have some interest, because it would make the composition quicker, which means that basically you can free some time to maybe explore, because sometimes when you are writing a piece, you have some time constraints, and you wouldn't feel open to like take time to explore like new ways. So with those AI assistants, it would be a bit easier to have some rough sketch and to maybe express yourself more quickly. And there's a problem we face when like building AI tools for musicians, is that the ML research, machine learning research, is not exactly built by musicians. And so often, so there's a gap between the two. And often, like ML researchers are more interested in building accurate models, which could be very complex. And on the other side, like musicians could be more interested in having accessible tools, which are really reactive. And also, like often these AI algorithms are not really interested or integrated within the artist's workflows. And so I think it's really important as a researcher to understand how musicians work in order to understand their creative process and to see how the AI can integrate within these workflows. And so the interaction for me is at the core of like the conception of these algorithms, because at the end you want the algorithms not to replace the artist, so not to take care of all the work, and also they shouldn't constrain too much the artist, which means that if you say, okay, if you want to use my AI tool, you need to follow this particular process, this could leave many musicians behind. And so it's really important to jointly develop algorithms together with the interfaces. And so now we focus more on the AI for piano music. So why, you could like wonder why piano music? And it's quite nice still because you can, at the end, if you are alone, you can still play a piece, a piano piece. It's quite handy and you have like important repertoire. And also composing at the piano can be seen as the first step when you are composing for other instrumentations, which can include like orchestral music or like quatuor music. Many ideas can be easily expressed at the piano. And also for the ML point of view, it's really interesting because you can get a lot of data. So you have like many scores, but you can have also, it's easy to gather data because you have like all these MIDI keyboards. And you have also automatic transcription algorithms, which are working quite well nowadays, plus a really important repertoire. And so this makes such a corpus quite interesting from the ML point of view. And also I'm a pianist, so I really like piano music, and so I think it's a nice excuse to do that. And so now we can, I will just do a quick review about the existing approaches. And so I will, it's a totally non-exhaustive review. So sorry if I forgot some approaches. And I will focus on these like AI systems, which are like accessible to musicians, because often it's hard for a musician who would like to experiment with those AI algorithms for music to know exactly like the current state of the art. And so here are the like 5 like projects I will be presenting. And so first, NonAuto. So it's a project I did with Daisy Bazin last year or 2 years before. And the objective was to have an interactive score, and everything is web-based and quite responsive with really simple controls. So here, like in the video I will show, you can see I can just simply click on any measure and to ask an algorithm to recompose this particular measure. And so it's called NonAuto because you are no longer writing notes, but you are just interacting with this algorithm. So let's have a look. And so each time I click, you have new proposals. And so now we can ask to regenerate the ending. And so it's like working smoothly. Like what's nice here is like the music is not interrupted, but it's not really expressive piano. Here it's more like score based, and it's a model which generates bar chorals, so it's a deep bar. A model I did years ago. But it's what's nice is that the music never stops and flows continuously. And so for musicians or for even real-time performances, it can be interesting. But you could still go a bit further with the integration. And so we did another model that you could connect with Ableton. So Ableton is what you can see on the right here, and it's a digital audio workstation, or DAW, and it's like common for artists to work in this kind of like software. And the idea here is like you have NonAuto proposing the score, like the basic material, and then you would work on the sound level within Ableton. And what's nice here is like you have the constant interaction between the two. So here, for instance, you have a simple melody based on a chord progression. And you can see I can click, and anytime I click, I have a proposal, immediately a new proposal, like the AI, but the sound is quite terrible. And so we can decide to route this into Ableton and to put some nice fluty sounds. And what's nice in Ableton is that you have all the capabilities from Ableton, so you can choose to work on the chords, you can choose to work on the melody, you can choose to add the drums, and create progressively your own maquette. And yeah, you can still click on the score, and it will change like smoothly. And you can also choose to do some bit of work on the chords, for instance, to create this kind of maquette. And so it allows creative usages, because you can depending on the sound and how you would process the sound, it could be really creative. And so here, for me, the creativity comes from how you would use this plugin instead of the plugin itself. But as such, it's not really expressive piano music, and it's just lead sheets or bar chorals. And so another approach by Google Magenta is called the Google Magenta Suite. And it's a suite of 5 Ableton plugins. And it's fully integrated within Ableton, so it's quite nice. It's really neat and good looking. And this plugin-based approach is really nice because you have all these small bricks, and it's then up to the artist to choose how to recombine them and to make something out of it. And so we can listen to the video, one of the presentation video from the Generate plugin. And so you click and you have immediately 4 tracks here that you can listen to. And you have all these melodies which are generated extremely fast. But in my opinion, the interactivity is a bit limited, because you're here, the artist would be more acting like a character, and so it is presented lots of examples, and then you have to choose from which you like and which you don't like. And also the generations here, they have a clear distinctive style, and it's not really expressive piano music. Another approach here, it's called the Pianogenie. It's from DeepMind, I think. And it's an original approach because it allows anyone to play the piano by only pressing 8 keys. And what's nice here is it's freely available. It's a web-based demo. You can access it online. And here is what I made yesterday. So it sounds nice. I think like you don't hear any wrong notes, and it's really highly responsive. So you play, you press a key, and you have immediately like a note which is rendered. But I think it could be a bit hard to feel engaged because it's quite hard to understand and to make the AI do what you want or what you would imagine. And so you feel like you just press buttons, but you can't really control things, and it could be a bit frustrating, I think. And also it's totally standalone, and so it could be difficult to integrate in a musician's workflow. And now, so like the two last approaches, and they are more focused on really expressive piano music. And so here is like the music transformer by Magenta team, and they have made this nice looking online radio, and you can hear lots of examples, and they are not curated, and they are of really nice quality. And so here, like yesterday, I connected, and here is an example for what you can hear. So I really think the results are quite impressive, and you also have a like collab to experiment with the model. But I think like it's really nice for ML researchers and to see like what these models are capable of, but not really targeted to artists because like collab and all these tools are not really things they are accustomed to use. And also you have like no integration within like digital audio workstations, and so you can just like download your MIDI file, for instance, and work on it. So the interactivity is a bit limited, and also in the collab you can perform two kinds of operations. So one is like continuation, so you can continue an existing MIDI piece, or you can perform a harmonization of a given melody. But still, if you have like to do a back and forth between like the collab and your digital audio workstation, it could be a bit hard or daunting to use. And the last approach is the Musenet by OpenAI. So they have you can use their web-based demo, and you have like the possibility to choose between many different styles, from Chopin to Bach to Beethoven. And the quality of the generations is really high standard. And so here is what I composed also yesterday. And so it was composed in the style of Chopin. It's really neat, but the only interaction you can do on this website is you can choose a specific instrument, specific style, and then click on next, and you have a continuation, which is proposed. And so again, like a limited engagement from the user, because you can't, you feel you just click and you wait. And sometimes it can take really a lot of time to generate. So for the examples I showed you, it took me more than 1 minute to generate, 20 seconds. And also it's like standalone, so you can just like play around with this and download the MIDI file. And I think it's really nice to experiment and to understand the model, but then it's not really usable for an artist. So now I will present my approach. And so the idea was to focus on the interactivity. And so for this, I decided to choose only one basic operation, which is called piano performance in painting. And the idea is as simple as that. You have a score and you just ask the model to generate a given region. And the model generates something like a plausible continuation, but which goes smoothly and nicely fits with the ending. And so with this, it's quite simple, really easy to understand, but it covers many use cases that you've seen before, because you can generate from scratch. You can generate continuations, but you can also do large edits of like big chunks. But you can also like refine your creations, and by just doing inpainting on smaller chunks of music. And so here is how it works when you integrate this into Ableton. And so you basically select a region within the Ableton editor, and you click on generate. And this is totally real time, and you have like a new proposal immediately. So all what you hear is generated until these last chords. And so the model was able to smoothly go from one part from the beginning to the end. It was smooth, it was fast, and the generations are like quite of good quality. And also you have a really simple interface, because you just have a generate button to generate, and you can also choose how much notes you would like, if you want like a dense, like a high number of notes per second, or really like scarce number of notes. And so I think like this simplicity makes it really accessible to artists, and it's also fully integrated within Ableton. So I think it's nice having a try. And so now it's the part where I just discuss like quickly how it works. And so first, so we have a huge corpus of piano pieces. And what's nice with piano pieces is that you can have the MIDI standard. And so the MIDI standard just captures basic information about like which key is pressed, so it's called the pitch, how hard you would press this key, so it's called the velocity, when do you press the key, the not on event, and also when would you release the key. And with such like basic like information, you capture quite well any piano performance, and then you can apply any like piano sounds on it, and it sounds quite neatly. And so it's a piano performance can just be seen as a sequence of such events. And so it's really nice. In fact, the MIDI standard was made for real-time performances, but for like machine learning, maybe it's not exactly the best encoding you could think about. And so in the literature, you have many, in fact, encodings which have been used. But in fact, it's really important to choose the right encoding, because it highly affects the learning task. And so you have like, for instance, you see like Lackness from Chris Donnell, where they generate like NES game music. They have a particular like encoding. Also, the music transformer has this not on, not off encoding. Musenet is a bit different, where they store many information about like the composer, like the instrument that we play, and also some information about the tempo, about the notes, etc. And you can divide these encodings into roughly two categories. One would be a duration-based, and the other one is the on-off based representation. So on-off, you would just put an event when you press a note, like here, and also have another event when you release this particular note. In the duration-based, it's a bit different because when you just say, I'm pressing a given note during a certain amount of time. And so here, and so you have to wait a bit between the events. So it's a bit different, but when you think about the on-off based encoding, in fact, it's like a parenthesis. When you open a parenthesis, you have to close it at some point. And so it's the same here. And in fact, it forces the model to learn a particular structure about the data. And finally, I think it's not really helping like the machine learning models to learn. And there are also two other categories. One could be seen as the one token is one note, as in the Musenet. So you can see here, like you could say, like one token is represented by a piano, which will play a G2 with a velocity 72. While you have other approaches, so for instance, like the pop music transformer by Wenyi Xiao. And they have split, in fact, a note between different attributes. So it could be pitch, duration, velocity. And they also add some other information about the beat structure and the chords. And so you have like smaller tokens, but with different meaning and different attributes. But there are like two shortcomings. They have shortcomings, all these approaches, because like if you say one note is one token, basically you are considering a huge alphabet, so many possibilities, because maybe G2 with velocity 72 would be different from a G2, but totally different from a G2 with velocity 74. And conceptually, they should be close, but if you are like doing this, it would be a bit different. So of course you can imagine other ways to cope with that. But essentially, it's a problem. And also with the on the other side, like the attribute equals token representation, you see there are a bit less structure because you can't even know what will be the nature of the next token. So when you are here, for instance, you can't say if it would be a pitch or like a beat token, and so you can also just make mistakes because you are predicting in the wrong category. And so the encoding we propose is just like really simple. It's just a structured sequence where you alternate between pitch, velocity, duration, and a time shift. And so it means like you could wait 2 seconds until the next note will be played. And once you have this, it's a bit easier because like you know exactly which category to predict. Also, you have smaller alphabets because each of these like categories, they live in roughly an alphabet of size 100. And also it's a bit easier to learn from because imagine you have like a piece and a transposed piece. Most of the tokens would be exactly identical except from the pitch. And so for like machine learning model, it would be easier to learn and also to generalize. And the basic thing we had to do to achieve this was to introduce a time shift of duration 0. So you always have a time shift every 4 tokens. And then we discretize time shifts and durations. But this discretization is almost impossible. And so we can try to just learn and train a model to do this like prediction of like standard prediction, sequence prediction. And so I train a transformer model with causal masks represented as those triangles. So it just means like if you want to predict this token, and this token has only access to what has been generated before. And so you can train this in parallel and it works well. And so with this like simple encoding and simple model, you can have really nice looking generations. So here is an example. It's a bit long, but I really like this example because I think it's really impressive. Because it's not natural in the way, like it's not really piano music because it's too virtuosic. Not all the generations are that virtuosic, but I think it's really like nice example. And so more precisions on this particular model. And so it's just an 8-layer linear transformer. So linear transformers were introduced by Angelos Kataropoulos in the paper Transformers are RNNs. And it allows to train on basically longer sequences and to have the same power of like regular transformers. I also made some architectural improvements. So roughly it means like adding some gating when you are merging the residual connections, and also putting the layer norm as it is now usual in the residual connections. Also, it's trained on the giant MIDI piano dataset, which is a dataset from ByteDance. And as usual in transformers, I just add the positional embedding, which means like each token also knows its location within the sequence. But now, since we have like this structure sequence, we can also add what I call channel embedding. So it's basically saying like this is the pitch, this is velocity, and so you know exactly what you would predict next. And I also add elapsed time embedding, which means like at any time the model knows how much time has been spent since the beginning of the generations, and so it helps the model in some ways. And then I perform the usual data augmentations, which means like you can transpose a bit your MIDI. You can also apply or speed up, or that's all. So really classical stuff. But now, how you can use this to perform in painting? And in fact, it's really simple. Also, now you have like these. So you have a sequence. And you will just mask some of the tokens. So it's like here, like what I call the constraints. So the stripes tokens, they are not visible, but you can still know like their classes. And it's a basic standard sec-to-sec architecture. And you implement this with a like encoder decoder transformer. But the main idea here is like a contrary to, for instance, a translation task, where when you are generating maybe like translation in French from an English sentence, you need to attend to all the words in the English sentence. Here, you only need to look in the future. And so this is represented here by the like anti-causal masks, because all the information of what has been generated before is also already present here in the input. And so, for instance, here, if you want to predict like this green token, you can know exactly like all the events that will come in the future, and also everything that has been generated before. And so it's called anti-causal, diagonal causal masking, so ACDC masking. And it's working just quite well. And so when you are training this, you can just generate random masks and you train it as usual. So some precisions, it's not a BERT model, because like the BERT model has like a bidirectional attention, and you don't have this sec-to-sec architecture. And in fact, it's more similar to the anticipation RNN articulated like years ago, where you have also an RNN meant to summarize what will come next. And so we have also to point here that this architecture wouldn't have been possible without the particular PIA representation, because this is totally infeasible if you have an unstructured or an on-off based representation. Because you can't do proper masking, and you have like some issues like that. And also like a diagonal cross attention is sufficient because you have a perfect alignment between your input sequence and the constraints. And also we can take fully advantage of the two inference modes of the linear transformer, because like recall linear transformers are RNNs. And so what's nice here is like you can perform process all the constraints once, and everything can be done in parallel because we have these anti-causal masks. And then you can perform an RNN-like decoding. And so what's nice here is like the generations will be really fast, and you can perform this in paintings. And so this model is quite flexible because you can perform unconditional generation if you mask everything. You can perform in painting if you mask out only some tokens and you only regenerate these tokens. And an example is like you can velocify, I would say, a given piece, because if you mask out all the velocity tokens, you can just regenerate this and it would be a slightly different performance. And it can be interesting in some settings, like for instance, if you are in Ableton, you can compose in Ableton, but if you have to also precisely set all the durations and velocities of the notes, it could be like painful. But if you just like put your notes and ask the model to generate like plausible interpretation, it could be like easier. And it's also particularly well adapted to the in-painting of contiguous regions, because if your region is contiguous, you can compute the RNN hidden state in parallel and in only one pass. And this means that in fact the inference time to generate a contiguous region would just be linear in the size of the in-painting region. And so this means that if you want to in-paint like the 4 last tokens, it would take the same time as in-painting the first 4 tokens. And this is quite surprising, because like if you just do this with an RNN, you don't have this capability. And this allows to have a fast and stateless server if you implement this. So to finish, like a small digression, which is quite surprising. It's like normally when you train the model, only the masked token are predicted. So if you mask this, you just predict that, and all the like constraints and the notes you already know and you don't want to regenerate, you don't learn, you don't train your model to predict this. And we can wonder what happens if you still generate those notes. And what's surprising here is like you could find the model would just copy the constraints. And what happens here is like it's not the case. And as you can see here, the two sequences, so here are generated with the same, exactly the same constraints, where you generate everything. And they have a similar structure because it's fast before and slow after, like simple statement. But they are like looking differently, and they sound different, and they are different. So we can have a like small look. So here is like one generation, so it's not like as good as a normal PIA, because like this makes no sense, I recall. And here is like the second one. And so it's interesting because they have different textures, but it's not just simply copying the constraints. And yeah, I thought this was quite surprising. So with like the model I presented, it's now really easy to integrate PIA in a DAW. And you have many benefits to do this because you have a rich ecosystem. You can you have plenty of instruments, virtual instruments, plenty of effects. It's a rich ecosystem, and it's a software like many artists use, and it fits well with this plugin-based approach where you have like all these small bricks, and then the artists choose how to use these. And so you could think about like fruitful interactions between this plugin and other plugins. And so you could, for instance, render a PIA generation with not with piano, but with an orchestra. And so this is Stefan Lettner who composed this with PIA. And so you can have immediately some rough idea, and it changes like working on the sound level changes everything. And so this allows to have really creative usages of PIA and all these AI algorithms. And so like the main way, the main important thing here is like the artist can choose and also invent how to use PIA and how to integrate it in their workflow. And so some remarks about like what was important here. It's like the reactivity of the model was crucial. And so if the generations would take like 10 seconds to just have one like proposal, I think it would just be a technical demo. But here, if you have immediate like responsivity and it's immediate generations when you click, it becomes a usable tool. And I think it's quite entertaining to see like all these notes appearing. And also you have to learn how to talk to PIA because you only have one button, and so it's highly dependent on what you will, like on the task you will ask PIA to do. And so it could be a bit similar to the prompt engineering you've seen with the GPT-3. And yeah, PIA is capable of providing really nice solutions and in many styles. And in our test, we also tested this on totally unseen like styles, and it worked surprisingly well. And so yeah, like just PIA will not change like how you make music, but I think it can enrich how you make music. And of course, you can't do everything with Inpainting, and it's just the first step of what these AI tools could be in the future. Here is a small recap. So PIA is just a transformer on a proper representation. The linear transformers are nice, and there is a nice combination between linear transformers and this in-painting task. And this allows you to have a really responsive, small algorithms that you can integrate into like a digital audio workstation. And a bit shorter recap is just like a PIA, you can try it. It's available for free. And it's just the plugin, so it's really like lightweight, easy to install. You go on the website, you can drag and drop, and you can use it in Ableton. And if you are on Windows or Mac, you can have an Ableton trial, so no excuse. If you are on Linux, I'm so sorry, but it should be easy to integrate PIA to other DAWs, provided you have access to the API of the DAW. I also make some videos on YouTube that you can simply find by like Googling Piano Inpainting Application, I suppose. In one, I demonstrate how you can start from scratch and generate in real time like just a piano piece. So many thanks to Leopold Krestel, because in fact this is based on our previous works, which was like the vector quantized CPC, compressive predictive coding, especially like the representation we've been using for more than a year now. Adrien Laversen, who helped me doing the Ableton integration with Ableton, Thais Bazin for all the ideas and experience, and also CSL for letting me do this research. So, do you have any questions? Hope you like it.
Thank you, Gaëtan. Are there any questions? Just one maybe from me is I'm curious to know how big is the dataset, the giant MIDI dataset?
I have not the figures in mind, but compared to the Maestro dataset, I think it's 10 times bigger. I think it should be around 10,000 MIDI files, but I'm not sure. I should check it. But they have a nice GitHub.
Yeah, okay, thanks. Alessandro?
Yeah, thank you. So Gaëtan, really my congratulations, because it's a really amazing work. I really appreciate it. I'm not sure I got all the details, but it really impressed me a lot. I have just one question. As you know, I'm involved in the so-called online training. So I'm wondering if a musician wants to set his own style. I mean, the machine could be able in future to learn while the musician works and to include his compositions and or in his style in your system, because it would be really interesting for me. Thank you.
Yeah, so for me, like it's not possible to do online learning with this, but I think it should be easy to, if you take an existing piece from an artist, you should be able to like do some in-paintings in the style, because PI is able to, I don't know how, but to adapt to the style, and so even to unseen styles. So it might be the case that if this like style is close to I don't know, like many styles in the data set, that you would be able to perform in painting that you like, that you think they are in your style, because you conditioned well the model. But also you could add like the corpus of this particular artist to the dataset, but it's not really online learning per se.
Okay, thank you.
Any other question for Gaëtan? Then thanks again, Gaëtan, for your participation. And I hope to see you next week for the next Etincelle seminar, which will be presented by Rick van der Zed, who will present us some work on plant phenotyping and digital twins of plants. So a combination of computer vision and plant modeling. Okay. Thank you very much. See you next week.
Bye.
Bye.